All right, we're on 6.2, periodic trends. And let's take a look at the warm-up. It says, what attractive force is responsible for holding the cloud of electrons in place in atoms? Well, isn't the cloud of electrons negatively charged, and don't opposite charges attract? So the repulsive, or the attractive force, I should say, that's responsible is going to be the positively charged protons in the nucleus. Number two, what effect would strengthening of that force have on the size of atoms? Well, if you increase the number of protons in the nucleus and you increase the positive charge, wouldn't that draw the electrons closer? And wouldn't that cause the size of the atom to decrease? Number three, what might cause a strengthening of that force? Well, I just said it. If we increase the positive charge in the nucleus, which means you're going to increase the number of protons, or you could refer to that as increasing the atomic number, because the atomic number increases left to right, row to row, period by period on the periodic table. Number four, what might contribute to a weakening of that force? Well, if you have fewer protons in the nucleus. Okay, so what we're going to be talking about today are periodic trends, how they influence the chemical and physical behavior of things, and it's all related to the electron configuration of an atom or an ion. And as we move across a period or down a group, we're going to notice some regular changes in elemental properties, and this is known as periodic trends. And the first trend that we're going to talk about is atomic size. Atomic size is sometimes referred to as atomic radius. This has to do with the outer boundaries of an atom, and it's going to depend upon the size of the charged cloud that the electrons are spending most of their time in, and we can estimate the sizes of atoms based upon how close they get to each other when bonds form between them. So if you take a look, I have two neighboring metal nuclei, and if you measure the distance between their nuclei and then you divide it by 2, that's going to give you something known as the metallic radius. So these are two metal atoms neighboring each other. Over here, if I have two chlorine atoms next to each other and I measure the distance between their nuclei and I divide that in 2, then I'm going to end up getting the covalent radius. That's half the distance between the two identical nuclei in a molecule. If you go to the next page, you will notice that there are two opposing factors that contribute to the size of an atom or the size of an ion. Now, if we look at the first one, the first one has to do with the number of energy levels present. That means the number of n's that are present. Remember, this was the principal quantum number n, and we labeled all of the periods in the periodic table with an n, 1 through 7. The more n's you have, the more time the outer electrons will spend further from the nucleus, and that causes the atoms to become larger. So n equals 1 versus n equals 7, these will be larger atoms, and these will be smaller atoms, okay? The second factor that's going to influence atomic size is something called the nuclear charge that is felt by the outer electrons. This nuclear charge is referring to the positive charge from the protons in the nucleus that the negatively charged electrons in the valence shell, or the outermost shell, can feel. Effective nuclear charge is referring to sort of the positively charged protons in the nucleus have the ability to sort of engage with the electrons in the outermost shell, and they can pull them in closer. So it's effective if that outer electron cloud is pulled closer and closer and closer to the nucleus, and that causes the atom to become smaller. They refer to this effective nuclear charge as ZEFF, okay? Now, of these two opposing factors that contribute to the size of an atom, the one that predominates as we move across a period or down a family is going to influence how the size of the atom changes. If you take a look at this image here, they're showing you that as I move from left to right, you will notice the atomic radius decreases, okay? And that's decreasing because the nuclear charge experienced by the electrons in the outermost shell increases. I'm increasing in the number of protons as I move from left to right. So since my positive charge in the nucleus is increasing and the electrons are going into the same shell, right? So they're experiencing more and more positive charge, which draws those electrons closer and closer to the nucleus, and that's why my atomic radius decreases. But as I go from top to bottom, my atomic radius increases. And that's because my n value is increasing. I'm increasing the number of energy levels, and that is causing the electrons to get further and further and further from the nucleus. And also, if this is the nucleus, and I'm just adding more and more and more n's, well, the electrons that are in, let's say, these energy levels, the n equals 2 and 3, these contain negatively charged electrons. They can repel each other and repel the electrons in the outermost shell, which makes that atom become larger and larger. So this is all summarized down here. As you move down a family or group, the size of atoms generally increase, and as you move across a period from left to right, the sizes of atoms generally decreases. Now, if you want a little bit of a further explanation of all of this, this first paragraph here is explaining as we go down a group what is happening, and these last two sentences here are explaining what happens when we go across a period in more detail. So let me explain. As you go down a group or a family and your n is increasing, you're adding an inner electron level between the nucleus and the outer electron shell. And even though the positive charge in the nucleus is increasing, each additional inner level of electrons effectively shields the outer cloud from the attractive force of the nucleus, and that is what is causing your atom to get larger and larger and larger. And these inner electron clouds are repelling each other, which makes your atom even larger. So one thing I need to note here is that if you go on to take AP Chemistry, do not ever mention anything about shielding. So do not use shielding as part of your explanation as to why the atomic radius is increasing down a group, because the AP Chemistry exam will not take it. Down here, as we move across a period from left to right, the electrons are being added to the same outer level. That means that the level of shielding by the inner electrons remains the same. And if you go to the next page, the added electrons are ineffective at shielding each other from the increasing positive charge on the nucleus. So the effective nuclear charge on the outer electrons increases, and the charge cloud is pulled closer to the nucleus, and that's why the size of your atom decreases. Here you will notice that the alkaline metals, which are here, these are the largest members of each period. So they have the largest atomic radius of each period, and they're furthest to the left in a period, whereas down here, helium, neon, argon, krypton, xenon, these are the smallest atomic radius for each period. These are the noble gases. These are in group 18. Furthest to the right in each period, okay? There are exceptions to these general trends, and it's usually going to appear when you're in the transition element. So like you'll notice that some of these atomic radii, they're kind of staying the same. When we're putting electrons in the D sublevels, the sizes are going to remain relatively constant. And that's really all that you need to know. Let's take a look at the quick check at the next page. Which of the two opposing factors that influence atomic size predominate as we move across a chemical period? Well, the nuclear charge felt by the outer electrons, this would be the effective nuclear charge, ZEFF, is dominating. And what is the general result? Well, the atomic radius decreases as the effective nuclear charge increases, moving from left to right. Number two, which of the two opposing factors that influence atomic size predominates as we move down? Well, that would be the number of electron levels or the number of ends, right? And what happens as I go down the group is that the atomic radius increases as the number of ends increases, okay? Number three, in general, is effective shielding most evident going across a period or down a family? How can you tell? This would be down a family. And that's because the atomic radius increases as I go down the group. And you've got your energy levels, your different ends, right? These are going to prevent the electrons in the outermost shell from experiencing the positive charge of the nucleus because they're kind of blocking that positive charge. If you take a look at forces affecting ion size down here, they want us to rank some ions in order from largest to smallest. And if you take a look at the periodic table, you'll notice that aluminum has 13 protons, okay? Fluorine has 9 protons. Magnesium has 12. Nitrogen has 7. Sodium has 11. Neon has 10, and oxygen has 8. But if I look at the number of electrons, Al normally has 13, but it has a +3 charge, so it has 10 electrons. And if I take a look at fluorine, fluorine normally has 9, but it has a negative charge. That means it also has 10 electrons. If you go back and you look at all of the ions, they all have 10 electrons. So if we want to put them in order from largest to smallest, the number of protons in the nucleus is going to influence our atomic or ionic radius, I should say, since they're ions, the greatest. So if I look for the one that has the most protons, which would be my Al +3, that would have the greatest nuclear charge, so that means it would draw the electrons in the most, so it would be the smallest ionic radius, okay? Whereas the one with the fewest protons, which would be the nitride ion. That one would have the largest atomic radius, or ionic radius, I should say, because it has the fewest positively charged particles in the nucleus to draw in the electrons, okay? Okay, take a look at, let's make a little note here. Actually, this is not in the book. If I'm comparing a neutral lithium atom with a lithium ion, they each have 3 protons. Neutral lithium has 3 electrons, but the lithium ion has 2 electrons. So there's more positive charge here to draw in the fewer electrons, so that means this would be a smaller atom in comparison to its neutral atom counterpart. So generally speaking, a cation is smaller than its neutral atom counterpart. Okay, and then if I'm talking about a fluoride ion versus a neutral fluorine, fluorine has got 9 protons in each. Neutral has 9 electrons. This gained one, so this has 10 electrons. So what that means is I don't have enough positive charge in the nucleus to draw in this extra electron, so the anion will actually be larger than the neutral atom counterpart. And I'm exaggerating the sizes here. So the anions are larger than their neutral atom counterparts. Okay? Okay, now that we're done with atomic radius, we can move on to ionization energy. Ionization energy is abbreviated with a capital I, capital E, and it is defined as the minimum energy required to remove an electron from a gaseous atom or ion. And the term is often used to mean the first ionization energy. You'll see a little tiny subscript 1 after IE. This is the general equation that you would see for the first ionization energy. It's showing you have a gaseous atom. This is the energy it takes to remove the electron from it. And then you're producing a positively charged ion because you're removing an electron. And then you have 1 electron getting kicked out on the product side. Now, this tells us how strongly an atom holds on to its outermost electrons. And things that have low first ionization energies are likely to lose electrons and form cations, whereas things with high first ionization energies tend to gain electrons and form anions, or they may not form an ion at all. One thing that you should know is, as atomic size decreases, the ionization energy should increase because it's going to be harder to remove an electron in a smaller atom where that electron is closer to the nucleus. Here I've got a graph showing you the noble gases that I've circled here. And they have the highest ionization energy of anything in their period. And that's because they have the smallest atomic radius. So their electrons are closest to the nucleus. It's going to be harder to remove it. Here I have my group 1 elements, and actually let's erase that. For my group 1 elements, you will notice they have the largest atomic radius of their period. And that means they have the lowest ionization energy because the electron is further away from the nucleus, so it's so much easier to remove. So you can see that the lowest first ionization energies are associated with the largest atoms, which are located in the lower left of the periodic table. The highest first ionization energies correspond to the smallest atoms, which are located in the upper right portion of the periodic table. Okay, lower ionization energies are associated with elements near the left side of the periodic table, namely the metals. This tells us that metals generally tend to lose electrons if we have a chemical reaction, whereas nonmetals have high ionization energies, so they tend to gain or even share electrons rather than losing them. And then noble gases do not do either of these, okay? So ionization energy is increasing in this direction, and it is decreasing in that direction. Now, there is an exception to ionization energy. All right, let's talk about the difference between nitrogen and oxygen. Even though oxygen is a smaller atom than nitrogen, oxygen actually has a lower first ionization energy than nitrogen does. If you look at the orbital diagram, you'll notice here that we have a pair of electrons in a 2p orbital. Why is that significant? Those electrons repel each other, and that makes it easier for oxygen to lose one of those electrons when it's first ionized. So this explains why oxygen has a lower first ionization energy than nitrogen does. If you turn to the next page, we can take a look at beryllium. Beryllium, if this is the nucleus, and this is the first energy level with 2 electrons in it, and this is the second energy level with 2 electrons in it. These are the outermost electrons, also referred to as the valence electrons, whereas this is the core electrons. They're closer to the nucleus, okay? So if I remove 1 electron, this would be the first ionization energy. If I remove this electron, this would be the second ionization energy. But the moment that I attempt to remove a third, now I've gone into the core, which is closer to the nucleus, and removing that electron is going to be even harder than removing the first 2 because it's going to require a lot more energy due to its proximity to the nucleus. So after removing 1 electron from an atom, further ionization energies tend to increase. And whenever you've lost the valence shell electrons, the next ionization energy that goes into that core is going to require a lot more energy. And here is the value that is associated with it. There is a tremendous jump between 1756 and 14,860 for the ionization energy. So that's a dramatic increase in the energy required to remove that third electron. And that reflects the fact that it's closer to the nucleus, it's in the core, and it's held on more tightly. If you take a look here at the practice problems on the next page, Number 1 says, rank the following alphabetical list of elements in order of decreasing first ionization energy. So argon is stable. I'm going to put that first, followed by sulfur, silicon, aluminum, magnesium, sodium, rubidium, and then cesium, which is furthest down and to the left. Okay, this is going to be the largest atom. It's going to be the easiest to remove an electron, so we'll have the lowest first ionization energy, whereas argon is further up and to the right. It's a smaller atom, and it's stable. It will absolutely not want to lose any electrons because it's got 8 in its outermost shell. If you take a look at number 2, members of this chemical family have the highest first ionization energy in their period. Well, those would be the smallest atoms, which would be those from group 18. Members of this chemical family have the lowest first ionization energy in their period. That would be group 1, because those are the largest atoms in the period. The last one, members of this chemical period have the highest first ionization energy in their family. That would be the first one. This is the uppermost period of a family. Last one, members of this chemical period have the lowest first ionization energy in their family. That would be number 7. Number 3, the nature of the 2s sublevel is such that 2s electrons have a higher probability of being found closer to the nucleus than electrons in the 2p sublevel. Consider this and the following electron configurations. Suggest a reason why boron's first ionization energy is less than beryllium's, even though boron is a smaller atom. Okay, well, the 2s electrons here spend more time closer to the nucleus than the 2p electron here. And the 2s electron could partially block the positive charge experienced by the electron in 2p. And this could make it easier to remove an electron from boron than from beryllium. Okay, last periodic trend is electronegativity. Electronegativity is often abbreviated capital E, capital N. It's the ability of a bonded atom to attract shared electrons to itself. Atoms with high electronegativities will pull bonded atoms closer to themselves. Atoms with lower electronegativity values will have their bonded electrons pulled further away. Smaller atoms would have higher electronegativity values because their nuclei are going to be closer to the bonded atoms than the nuclei of larger atoms. And the trends that you see in electronegativity are really similar to those seen in ionization energy. What that means is electronegativity increases left to right across a period, and it increases moving up a group. Okay? The noble gases don't have any electronegativity values because they don't tend to form chemical bonds. So if you take a look at the next page, here you want to earmark this page. you will use this page as a reference for obtaining the electronegativity values for further sections. You'll notice the noble gases, which are the group furthest to the right, they don't have any electronegativity values associated with them, okay? Electronegativity values are ranging from 0.7 for francium all the way up to 4.0 for fluorine. I believe these are also on the back of your book. These values were determined by Linus Pauling, and the trends indicate that metal atoms, which are large, are going to have low ionization energies and low electronegativity values. So here you'll see in this figure, lithium, sodium, potassium, rubidium, cesium, francium. These are your metals, and they are larger metals. These are all from group 1, and they have low electronegativity values. Their nuclei are further from the bonded atoms. Up here, fluorine, chlorine, bromine, and iodine, these are the smaller non-metal atoms. These are actually the halogens. And they have higher electronegativity values because their nuclei are closer to bonded atoms.